Hello guys, welcome to the channel. In this particular video, we will be looking at the cake distribution problem. So let's see what it says. Here is the problem, and it says that Geek is organizing a birthday party, so his friends brought a cake for him. The cake consists of n chunks whose individual sweetness is represented by a sweetness array. So we have a cake consisting of n chunks here. So let's say I have 6 chunks. This is how the cake looks like, and now each value in the chunk is basically represented by the sweetness array. So if I consider this sweetness array, then I will have the sweetness of each chunks as 3, okay, 6, 3, then 2, then 8, 7 and 5, right? Now it says that at the time of distribution, Geek cuts the cake into k plus 1 pieces to distribute among his k friends. One piece he took for himself. So this cake is basically going to be divided into k plus 1 pieces. And each piece consists of some consecutive chunks. This is very important, guys, because this gives us an idea that we are actually dividing this cake into k plus 1 consecutive chunks, or I will say we are dividing this array into k plus 1 sub arrays, right? K plus 1 sub arrays. And now it says that you need to find the maximum. Okay, before this, have a look at this. He is very kind, so he is left with the piece with the minimum sweetness for him. And now you need to find the maximum sweetness that Geek can get if the cake if he distributes the cake optimally. Let me tell you what it means. It means that we are given an array sweetness, and we have to divide this array into some sub arrays, k plus 1 sub arrays. So here the value of k is 2, so I need to divide this particular array into 3 sub arrays, right? And for these 3 sub arrays, I will have some sweetness of each chunk. Let's say I have this chunk. So the sweetness of this chunk is going to be sum of these two values, which is 9, right? So this is the total sweetness. And this way, there are multiple like possible combinations. There are multiple way to make k plus 1 sub arrays. Let me explain how. The first one is take these three values, then take this 8, then take this 7, 5. This way I will have 11, 8 and 12, right? And there is one more way. Take this 6, 3, then 2, 8, 7, then 5. This way I will have 9, then I will have 17 and then 5, right? So this is one of the possible way, and one of the possible way is take 6, 3, then 2, 8, then 7, 5. So it is 9, then 10, then 12, right? And for this there are multiple combinations like this, right? So among all the possibilities, consider the minimum of each possibility. For this the minimum is 8, for this the minimum is 5, and for this the minimum is 9, right? And there are multiple possibilities, and among all of these minimums I need to return the maximum sweetness that Geek can get. So isn't it similar to this problem? The problem statement simplified will tell us that we are given an array, and we need to divide this array into k plus 1 sub arrays and maximize the minimum sum. This is what we need to do. Now for this particular example, as this is the most optimal distribution, so the answer is going to be 9, right? Now I hope you have understood the problem well. So let's talk about the solution. Okay, so I'll start with the brute force approach, and brute force approach is going to be pretty simple. Before this, have a look at the constants. And this is very important. I know that the value of sweetness is going to be in the range from 1 to 10 raised to the power 9, right? So I can try out all the possibilities from in this range. I can try out every value, and I can check whether this can be my possible answer or not. Let me explain how. I can start a loop for I equals to, okay, I'll start from the back. Let's say from 1 to 10 raised to the power 9. I have the values like, first of all, remove this. I have the values 1, 2, 3, 4, 5, 6 and up to 10 raised to the power 9, right? So if I start from this point, then I will check whether this can be my answer, whether this can be my answer. For now, just don't think about how to check this thing, but just have a look on the concept. So I'm checking all the values, and let's say this is for this the answer is true, this can be my answer. So I'll not stop at this point. I'll check for maximum value as well. Why? Because I need to maximize the minimum value. So this loop is going to give us the maximum value. But think of one thing here, that instead of checking from the this direction, I'll start from this particular direction, and whenever I found first value which is going to be my answer, so I'm sure that this will be the maximum value possible, because after this the value is decreasing. I hope this makes sense to you. So I can start a loop. I can start a loop I equals to back, so 10 is to the power 9, and then I will do I is greater than equal to 1 and I plus plus. For values in this range, I am going to check whether my current value can be my answer or not. So I'll check I. So this I will talk about this particular function in detail, but first of all, just have a look at this. So if check of I is true, then answer equal to I. And after this, okay, so instead of even doing this, I can simply do one thing, that I can return answer. So I will return answer. Fine. And if answer is not valid, in that case I can return -1, right? So this is how we can approach this problem. Now the question you are gonna ask me is, hey, how to check whether the I can be my answer or not? But before talking about this, first of all, let's see what does this check actually means. This check actually means that I'm checking whether I can be my minimum sweetness or not while making the k+1 partition. This is what it means. Even let me I have written the same thing here, how to check whether the particular value can be my answer or not. But first of all, let's talk about check function. So check function is basically okay, check function is basically checking that whether I can be a minimum value while making the partition, right? This is what it means. While making how many partition? While making k+1 partitions, right? Pretty simple and straightforward. Now we are going to talk in detail about this check function. This check function is going to check this, right? And we have the value I which comes from the parameter of this function, right? Now what I'll do is I will keep try. I'll start a sum from his sum from this point, and sum is initially 0. And you can see that let's say I have the k value as 9. I am checking for 9. So I'll come to this point. You can see that the sweetness is 6 here, right? So I'll move further, and then I will add this value as well. When I combine these two, then the sum becomes sum plus equals to sweetness of I. So let's say sweetness is array, so array of I, right? Okay, let me remove this array of I. This is what I'm doing, and here you can see that the sum becomes 9. Sum becomes 9 at this point. So whenever my sum becomes equal to this k, at that point I need to apply break. Why? Because I want my minimum value to be 9, and if I add the value further, in that case I will have the value greater than 9. This is not something that I want. Fine. Now I'll make, after this partition, making a partition simply means that I'm again starting the sum from 0. So sum will become 0 at this point, and count will increase. So initially, let's say I have made 0 partition, so now my partition will become 1, that I have made 1 partition, right? Fine. So now move further. You can see that the here I have 2 and here I have 8, right? So the sum of these values is basically going to be what? 10. So whenever I have the sum greater than 9, in that case again I will put a partition. Why I'm putting partition? Because I don't want my value to be greater. Okay, this is very interesting to explain why I'm putting a partition here. Since my value is greater than 10, so I have got one greater value, right, which is greater than 9, and I want the minimum value to be 9. So I will put a partition just after I have got the greater value. There's a reason while doing this. In When I do this, in that case I will have the maximum possible partition, maximum possible partitions. But hold on, you will say that, hey, we just want k+1 partition, so why you are moving towards the maximum possible partition? I will surely tell you this thing, but first of all, let's complete this part. So I'll put a partition again, and this way I have two partitions now. And after this, I will move here. You can see that here I have value as 7, right? And here I have the value as 5. So when I combine these two values again, then I will have my answer as 12, right? So I can again put a partition here because this is something greater than 9. Fine. So till now I have put a 3 partition, right? And how many partition we wanted? We wanted k+1 partition, which is 3, because okay, this is not k value, let's call it well, and the value of k for the previous example was 2. So I wanted k plus 1 partition, which is 2 plus 1 is 3. So I wanted 3 partition and I have made 3 partition, right? So for 9, the answer is going to be true. And how I'm checking? I'm just checking whether count is basically going to tell us about the partition. If count is equal to k plus 1, fine. And for this, what I'm doing here is I'm simply checking one thing, that first of all, I'm iterating over all the elements and I'm increasing the sum. Sum is going to be array of I, increased by array of I, right? And if our sum becomes greater than or just equal to, this is what we checked here, right? Greater than or just equal to the value that we have. In that case, we will put a partition, and putting a partition simply means that sum becomes equal to 0. And after this, my count increases, so count will increase by 1, right? This is what we need to do. And when this loop completes, this is loop from I equals to 0 to n. When this loop completes, I will have the answer. But hold on, we were running towards the maximum possible partition. Let me tell you why. In order to understand this, I'll write one more example. So this is not correct, but this is something that we have figured out till now, right? Just don't think that this is the correct code. I will tell you along with the intuition. So let's say I have the example 63285414, and I have to put the partition for like value is equal to 6, right? And again, I am concerned about only two partition k equals to 2. So let's see how we can do this. I will come to this 6, and as this 6 is equal to value, then I will put a partition over here. Fine. Now I will move here. Then I have 3, 2, 8. So I will again put a partition over here, because this is something which is again greater than 6. Fine. And after this, I will put I have 5 and 4. So this is 9. This is again greater than 6. I will put a partition over here. And for this, I have the sum as 5. Right? Okay. So let me change the color for this. I'll make the color as red, and for this the sum is 5. For this the sum is what is the sum? For this the sum is basically a 9, and for this the sum is 13, and for this the sum is 6, right? Now you can see that I was checking for value 6 and I wanted my maximum value to be 6, right? Okay, and how many partition I have made? Here I have made 4 partitions, you can see here. And special thing about 4 partition is, okay, hold on, you can see one more thing here, that I'm not having the minimum value as 6. Here I'm having the minimum value as 5, but still I'm going to have my answer as 2. How this is going to happen? So in order to understand this, what we can do is we can combine these two partitions, right? And when we combine these two partitions, then I will have the actual partition like this. I have 6, 13, and then I have 14 here. And for this, the answer is going to be true. You can see that the minimum is 6 and partition is 3, right? So whenever we have greater partition, than k plus 1, in that case, we can combine those partition. So this means that my answer should be true for count greater than equal to k plus 1. I hope this makes sense to you, right? So this is what we can do. This is the whole code that we are going to run, right? This is the whole code. So I hope now it's clear to you. But let me tell you one thing, that this code is not the correct code. It is just relevant to the problem. Like if I talk about this code as a an standalone code, like I want, let's say, okay. So in order to explain this, first of all, let me write this. This is not correct, but relevant to the problem. Not correct as standalone code. Standalone code, right? So what does this mean? I will tell you, but it is relevant to the problem and going to work for the problem, and your answer is going to be submitted. I will explain this thing. Relevant. Okay, so this means that let's say I want to check for the given example. The example was 632875, right? I want to check for this, and you can see that I have this particular example, right? And for this, I'll start with this point, and I want to check for value equals to 8. What should be the answer for value equals to 8? Okay, let me make this value before explaining this. Let me make this value as 10. And now I want to check for value 8. So I'll start from this point, and 6 plus 3 is going to be 9. So at this point, I will put a partition. I'll put a partition over here. And again, 2 plus 10 is going to be 12. So again, I will put a partition, and for this 7 plus 5 is going to be 12 again. Okay, this is 12, right? This is how we can put the partition. But am I having minimum value as 8? No, but it is going to give us the right answer. It is going to give us return true, right? Why this is happening? Why this is happening? This is happening because like we have written the code in this way. It's pretty simple, but why this code is going to work for the problem, for the given problem, right? You can see that at this point our code is not giving the right answer, but still it is going to work for the problem. The reason is you can see that we are having all the values as greater than 8, right? This is what we have figured out till now. And if all the values are greater than 8, then I'm sure that my 8 will not be my answer. So this is how cases like this are going to be avoided. Why? Because value greater than this value will be the answer. You can see that for this the answer must be 9. And even if I have a three partition whose sum is like 15, 17 and 18, and we were checking for the value 12, so for this the output will be true, but that doesn't matter because the actual answer is going to be 15, right? And even greater than 15 is also possible, but 15. So this is how this problem is going to be solved. Now I hope you have understood the main code that I have explained you here. So this is the main thing that I've explained you. Now let's talk about, oh, okay, so talking about the time complexity of this approach. So time complexity is something which is O of, first of all, I'm running this loop, right? And what is this range? This is the maximum value that we can have. So I'm running a straightforward loop to m, and after that I'm again running one more loop which is n loop. So for this I'm running a loop which is n, right? This is what we are doing. And for this the answer, the complexity will be this, and this is not going to work for the large inputs. So let's see what optimization we can do. It is pretty simple to understand the optimization. I was checking the answer in the range from 1 to 10 raised to the power 9, right? Fine. So values are like 1 2 3 4 5 6 and so on up to 10 raised to the power 9. See the beauty of this line. The beauty of this line is I'm having the values in the ascending order, right? Ascending order. And special thing is whenever we have the ascending order or the descending order, or I will say the sorted order, in that case I can apply something like binary search. Binary search. Okay, this is not again true for all, but I can at least think of applying the binary search once I have the sorted data, right? So how we can apply the binary search? Let's say for this the answer is true. For this the answer is true. If the answer is true for this, in that case, I am sure that I have to move in this direction, right? Because I want the greater value. So I can eliminate this. Let's say this is my low and this is my high. This is how the binary search works. This is my high. So I'll come at something in the middle. I'm not saying that this is the middle, but let's say I'm coming at this index, right? So for this index, if I check the answer and answer is true, in that case I will move further because I want to maximize the answer, right? So I can eliminate checking these values, you can see here, right? This is how binary search works. But what if the answer is false for this? If the answer is false for this, then the answer is surely going to be false for all the values in the front. In that case I can simply move backwards. This is how I can write something like binary search. Let me tell you how. The low is obviously going to be 1 and the high is going to be 10 raised to the power 9, because this is the range that we have. And after this I will check while my low is smaller than equal to high. This is how we perform binary search, right? I hope this is already clear to you. And after this I will look for the middle index. So my mid is going to be low plus high by 2. High by 2, fine. And inside this I will check if my check answer, if my check for mid is going to be give me true. In that case I will store this in my answer. So I'll write answer equal to mid, and I will move to right direction, right? This is low, this is high, and this is mid, so I will make my low equal to mid plus 1, and I'll check in this part after this, right? So I will make my low equals to mid plus 1. And if this is not true, then I'll write high equals to mid minus 1. Pretty simple, pretty easy. Now I have you understood this thing, so I can simply return my answer. Return my answer. This is what we need to do. Now I hope you have understood everything related to this problem. So now I'm just going to show you the code. Let me show you the code. This is the code that I have. On the left hand side I have the Java code, and on the right hand side I have the C++ code and the Python code. So you can see here how it's working. I have written the same function which is going to check whether it is good or not. Okay, so I have written the function name as good here. You can write the check function as well. And again, Inside this, I'm performing the binary search. I'm not going to show you the answer for the like linear search, because this is not the optimal approach, and I think the idea will be clear to you. And this is the implementation in Python. So this is all about this video. If you guys like the explanation, then you can hit the like button, and if you are new here, then you can subscribe the channel. Thank you.